Let's do, people, continue with inverse trig functions. Last time we did the fun part. Today we're going to do the boring part. I'm kind of biased on this. But those are definitions of trig identity, of inverse trigs, how they were created, and so on. The fun part, what I'm talking about, were derivatives. I don't know. I like derivatives. Derivatives, here you go. Derivative of arcsine, 1 over square root, 1 minus input square, cosine minus, secant, 1 over square root, input squared minus 1. And tangent is the best because you don't have to remember the order, or a square root is missing. 1 over input squared plus 1. So you need to know these. They will be all over exam calculus 1, 2, and 3. We practiced last time, and now I will help you with homework, which actually asks complicated questions about the domain, range, and so on. So inverse trig functions. I give you this table in my notes, but if you want some brief notes, make a table, make one graph first. That is going to be sine. Sine looks like this, right? And let's keep going, but we only need this part for now. Sine has domain from minus infinity to infinity, but it has a fixed range. The range is a tunnel, from minus 1 to 1, right? So sine and cosine cannot jump outside of minus 1 and 1 because it's a unit circle. Unless it's multiplied by 2, then the tunnel multiplies by 2, and so on. That's a change. But we try to find arcsine. Arcsine is the inverse function of sine. We did that before. This is the idea. Sine of arcsine gives you input, or arcsine of sine gives you input. Inverse functions. However, there's a theorem that tells you that not all functions have inverse functions. The functions must be one-to-one or passing the horizontal line test. Do you know about anything about horizontal line test? There's a vertical line test about the function being a function, right? Something being a function. Horizontal line test checks if a function can have inverse. So horizontal line test means here's my cubic function, x equal x cubed, right? Y equals x cubed. You put horizontal lines, and everywhere it should touch the function, not more than once. Yeah, it has an inverse function. Do you know what is it? Thank you. Finally, someone like cube root of x, right? So, oh, it has it. Look at that. How amazing is that? Well, sine and cosine look like this. How in the world we created arcsine and arccosine? It doesn't pass horizontal line test. Moreover, it actually has infinitely many points when you use horizontal line test. So it's not supposed to have inverse function. And people figure out what to do about that. They decide to restrict the domain. So you can make a note. Sine and cosine, sine x, cosine x, even tangent x, even though it's a chair, but it's infinitely repeated chair. It's actually looking like this guy I said here. But tangent x, it has two vertical asymptotes, and then they repeat it again. Still doesn't pass horizontal line test. So sine, cosine, tangent did not pass the horizontal line test to make sure they have inverse functions, because we really want to undo them. We really want to know what input gave me that angle, and so on. What angle gave me that output, right? Yeah, that's the correct one. Sine of what angle gave me 1? Sine of what angle gave me 0? We really want to undo that. So we're going to use restricted domain. Yes?
So the horizontal lines, would that be a way of saying, so every output has only one input?
Exactly. Horizontal line test says for one input, I have one output. Yeah.
Wouldn't that be a vertical line?
Vertical line test and horizontal line test, they work together to make sure one input has one output. So in this case, if let's talk about this. Okay, I'm not gonna put it. It's a good question. Let's talk about this case. Here it is. It's not a function because it doesn't pass vertical line test, but it has inverse because it passes horizontal line test. Together, they create function that has inverse.
Oh.
Very smart question, yeah.
Okay.
So let's do it. They decide to restrict the domain. It's called restricted domain. And this is how it looks like. Let's not look at sign everywhere, not from minus infinity to infinity. Let's only look at from minus pi over 2 to pi over 2. So we start from minus pi over 2, including it. Well, it's actually over here. And then we use plus pi over 2. On this restricted domain, does it pass horizontal line test? Yes. Because it's right before it wants to turn back to be repetitive. So, do you know how to create an inverse function we just covered before? Do you know what I'm doing? Do you know what I'm doing? Yes, it's a line called what? Y equals x. Amazing. And then, well, it's a bit too thick, but you got a point. Then you reflect it nicely. Whatever was looking like this will look like this. Going up now will go down, concavity changes, and that's how the graph on the right was created. They almost look the same, but they're not. Arcsine, here it is beautiful in blue. Arcsine is the inverse of sine, or sine minus 1. Remember, inverse functions switch domain and range with the original function. That makes sense because when I draw y equals x, let me put it here, y equals x, when I draw this line, I'm exchanging x with y on the restricted domain. So input becomes output becomes input. Thus, domain minus pi over 2 becomes a range, and for the inverse, and then output or range becomes domain for the inverse. So that's exactly the idea, how they exchange, like so. So, arcsine does not exist outside of minus 1 and 1, see? While sine does not exist outside of minus 1 and 1. And those are now basically restriction flipped, right? We kind of turn it. While when we restricted the domain from minus pi over 2 to pi over 2, range end up to be, here it is, range from minus pi over 2 to pi over 2 as a number. You maybe feel confused about, wait, why minus pi over 2 is over here? Well, actually, it's not confused. It's still a circle. But you can also always see it as a number. 3, 14, 59, blah, 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 over 2 is a number. So output is from minus pi over 2 to pi over 2. Same idea with everything else. You're not required to remember all of these graphs, but you need to know the idea of what is happening. For cosine, they decide not to do the same thing with minus pi over 2 to pi over 2, or else it doesn't pass horizontal line test. So they just shift it to the right. They decide to stick with 0 and pi for cosine. Then it passes horizontal line test. Check it out. And the inverse was created exactly the same way. Now the domain for the arccosine is minus 1 to 1, but range is 0 and pi, because domain of cosine was restricted to 0 and pi. In trigonometric classes, there's a whole class called trigonometry class where people are studying trigonometry for 4 months. It's super boring. I don't know. It's just hard. I was offered to teach it, and I'm like, yeah, no, thank you. They force you to remember all of this. What is a domain? What is the range of all of this? As a mathematician, I did remember them all. But to be honest, it's a very unnecessary memorization. You just need to know that arcsine does not exist from minus infinity to infinity like sine. Moreover, sine doesn't have inverse from minus infinity to infinity. It has inverse on the piece. Either it's from minus pi over 2 to pi over 2, or add 2 pi, or subtract 2 pi. Their inverse exists. Tangent is infinitely many chairs, right? Remember that. And they all have those vertical asymptotes that they will never touch. Here they are. Keep repeating. Well, then it doesn't pass horizontal line test. So we decide to keep only one, the one in green over here. That one is easy to remember. From minus pi over 2 to pi over 2. Easy to remember because tangent doesn't exist at pi over 2 minus pi over 2. If you don't remember this, there's a cool way to remember that tangent x is sine over cosine. Well, at pi over 2 and minus pi over 2, cosine is 0. Division by 0 happens. And that's why it has vertical asymptotes there. If you check limits, as we learned before, it will show you VAs. So when you flip this chair, it becomes, if you tilt your head, it becomes a horizontal chair. Now the chair looks like this, and now it's in the tunnel from minus pi over 2 to pi over 2. Range for the tangent was minus infinity to infinity. It's not restricted from minus 1 to 1, like sine and cosine. So now domain is from minus infinity to infinity, and so on. This is the ideas here. Yeah?
In the domain for tan x, it's given in square brackets, but aren't there asymptotes?
Very good point. Do you think we should include these or not?
No.
We should not. So, oh, actually, now you reminded me. I have it in my notes here that this table is wrong. See, you have to be smart enough to see mistakes in the book, or the scientific group tells you something and you're like, yeah, that's not true. So you need to be not only smart enough, but brave enough to mention that. That's what I think education is about. You should question computer as well. ChatGPT makes mistakes. We just were talking about it yesterday with my online calculus 2 classes. They were asking some simple questions about inverse and stuff, and it just made mistakes. So you need to be smarter than that. Oh, good job. That's amazing. These don't. Why would you include infinities? That's all super weird. And so on. Yeah.
Is it going to be the same for others, or are those points also?
Let me see. Others depends. Others sign.
I think others are fine.
Others are fine. Yeah, because sine at minus pi 2 pi over 2 are okay. So
All x's.
yeah, these are fine. 0 to pi is fine. 0 to pi is fine. Yeah, thank you for checking. That's very cool. Very cool. I'm actually like high respect that you also can point it out, right? This is like a question of authority, not me, but the book. Can the book be smarter than me? And then it's pretty cool that you're actually questioning. That's a very nice self-confidence. I like that. Yes.
For a function to be invertible, even in a restricted domain, doesn't the function have to be bijective?
Yeah.
Is it enough if it's just injective and we can invert the function anyways?
Yeah, it's fine with that. But to be honest, in upper level maths, they require bijectivity, and then they talk about more. Oh, that's a good question. Yeah. So these derivatives, you need to remember, that's not nothing new. I already showed you that last time. You need to remember sine. Cosine is just minus, so I don't really see a problem with cosine. Just like before, cosine gives you the same thing, but with negative. Now, tangent, and I'm talking about not sine. Arcsine, arctangent, and arcsecant. That's the one we require you to know. Arcsecant in the formulas often has absolute value of x. We're not going to be using it in this class. It's a more general case, to be honest. So in this class, it's fine. You'll be surprised, but the first week of calculus 2 class, boom, they're back in your face. In your face. We're going to be doing rate integration at the end of this class, but calculus 2 starts with that. So we usually review it in the lecture 0. That means you better remember it, basically. That's what I'm talking about here. And, and I want to show you something awesome before we practice more stuff. But I'm always very honest about what we expect you on the test. Other instructors might put arccosine and arccotangent. I don't do that. Those are 3, the most important one. And you can find the other one out of those 3. You know those 3, you get your A. I'm fine with that. Yes?
So why are we ignoring the absolute value of x?
Oh yeah, that's interesting. It kind of depends on the input. So this restriction matters, and sometimes they include this restriction, sometimes not. In general, it is taking into account more cases than what we cover in this class. I think it's, as I remember, it's something to do with this. So obviously it should not be plus and minus 1 because of this, but sometimes they also add the sign of secant. So if arcsecant now shows up, we should not mess up the sign, blah, 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 and divide by absolute value of x. I remember at some point I checked what was with it, and now I don't remember anymore. It's kind of boring. Just like you, I was curious, so I checked it out. Yeah, you should check it out. We can post it in the forum. What's the good explanation? Okay, so maybe erase that.
Can we just write
X.
what the absolute value of x when differentiating it, or do we just write one value without x?
I would not write it right in this class. Also, I think it will mess up a little bit with your differentiation. So Yeah, I can check it later and tell you why we don't use it. Actually, don't know. It's not. I'm not the one who decides. Especially when it comes to American education, we receive it, we teach it. I'm not sure like who makes decisions on that. And to be honest, I don't think anyone knows. Someone made a decision 15 years ago, and now everyone doing that. So I'm gonna show you some cool stuff, and we move on with derivatives. You kind of supposed to know the angles. I know it's super boring, and it's hard for many people who have bad memory, but you need to know the angles. 0, pi over 2, pi over 6, pi over 3, minus pi, 3 pi over 2. Need to know those guys. And then we're going to be learning areas in this class. And as you can see, the more we grow, the more area we accumulate above the yellow line. Do you see it? And below the yellow line. So that's how sine and cosine accumulate the unit circle. Check it out. In this case, it's sine. Check it out. How cool is that? Oh, in this case, there's a cosine. It's just purple. I did not even see it. The coloring choice is not good. Now, another cool thing I wanted to show you. So here it is. Here's your picture, sine and cosine. The question is, if I have this graph in front of me over here, and I stop at some point over here, here is the answer. Here is the answer, say it is 3.17. But it is sine. So sine of what angle gave me 3.17? That's what inverse function is about. You have the height. What gave me that height? And with angles, it has so many applications. The light comes from the window, the angles of the building you're building. Civil engineers were doing it all the time. So you already know what they want from you to build. Angle, what angle will give you that result? And that's the inverse function. And also remember the idea, sine is height on the unit circle. That's like small review. And cosine is length. Remember that, right? Like that's the whole point. And then the Pythagorean theorem and right triangle. And then I wanted to show this. Oh yeah, that's one of my favorite ones. As you can see, sines and cosines, they are oscillating, give oscillations. Basically, they're periodic functions, which means they are waves, sound waves, water waves, even color waves, because color tend to change, and so on. So the bigger the circle, the bigger the wave is. And that's where noise-canceling headphones ideas came into the picture. They're using inverse functions in your noise-canceling headphones. They detect small waves coming into your ears. What are those? Guess. If they're sound waves, they detect the small ones. What are those? Noise. So when you record singing of a bird in the yard, there will be noise around, a wind, and the leaves are moving, some kids are crying in the background. It records the small waves, finds the inverse of it, sends it back, and undoes the noise. It cancels the noise, literally how we're doing it. They're using Fourier transforms and stuff, if you're curious about that. We're gonna go a little bit to that in calculus too. But it keeps the big waves, because the big wave is what matters. And that's how noise canceling is happening. Yeah?
I'm pretty sure they don't use inverse functions because they shift the phase by 180 degrees.
Yeah, I know, but I know that it's just a little bit too detailed to explain. That's why I don't like to go into. They use Fourier transform, and Fourier transform.
High frequencies out and
they use but the Fourier transform undoing things, so it goes to the whole chapter of inverse functions. It just doesn't do the arcsine thing. I just don't want to go into that. Yeah, you're right. But I want to explain the whole idea of inverse problems. And inverse problems is not just arcsine or log or out of E. It's how to undo stuff, including the phase, sound. We do image processing and cleaning the image from the noise, pixelation, and so on. It's a very fascinating topic. So I'm glad you liked it too, because I think it's very cool. Unfortunately, we don't teach Fourier transform in Calc 1 or 2 or 3, but we do go to Taylor series a little bit.
You can use Laplace transform?
Not even that. So you do it later in your physics classes and then later in math classes too. But Fourier transform is everything. That's the one. Okay, that one is not here. Oh, okay. I guess it's a little bit here or not. Yeah, too slow. But we can check it later. Oh, here's your series. I already see. Fourier series, this is what basically you're going to be doing in your career. If you stick to engineering or physics, you cannot survive without Fourier transform. Look at this. Sine and cosines can not only have small or big waves, it can have waves inside of the waves. How cool is that? That is also pretty cool. And then in this picture, actually, you see how it approximates or being approximated by polynomials and stuff like that. We're going to do a little bit of that in calculus 2. And this is how people work with waves. They see big waves and smaller and smaller and smaller and smaller are noises, and they get rid of the noises. But also, how do you know which wave is which? Cosine multiplied by 5 is bigger than cosine multiplied by 3. But also, cosine of 3x is not the same as cosine of 5x. That's how many wiggly pieces will be in the interval, then how big pieces will be in the interval. All of this called transformation of graphs, and we learned it in pre-calculus class. So all of this so small annoying information gets into this big picture, which is used everywhere to predict waves. Earthquakes actually is a very famous inverse problem. Usually we see the earthquake happening too late, and people have a couple minutes to hide. What caused it? That's an inverse problem too. Tornadoes, we usually see it too late when a tornado happens. People from Kansas probably know it really well. And what causes it? Those are famous. I mean, we know what causes it, but why we cannot predict it ahead of time? That's the inverse problem here. So that's all done using some kind of inversing processes. And in trigs, we're learning it as arcsine, arccosine, and stuff like that. Oh, this is what I want to show. The more angles there are, the more little wiggly parts we have. And there's so many cool things that can be connected to that. So let me do one more example, and then we can move on to the quiz. I wanted you to be really, really good with derivatives of trigs. We have quiz today. There was an announcement. The quiz is long, so I decided to give you time due tomorrow. Don't panic about it too much. It's not too long, but it's a bit longer than usually. So I thought it's kind of rude to expect it to you tonight. And I don't want to be rude, so I moved it due tomorrow. One last thing, since my quiz today is mostly about derivatives, it doesn't have trigs. It doesn't have arc trigs, so inverse trigs. It has trigs though. But in general, after knowing all of this amazing information, oh, probably it's glitching. I need you to know how to take lots of derivatives. Not because it's my favorite thing ever, because it's on the test. But also taking derivative is important. Derivative answers lots of questions. How fast something is changing, how much it's wiggling, how much it's dispersing, how fast it is decaying or expanding. So expansion, we're going to learn it in calculus 3. Expansion, viscosity of honey, how much the viscosity is changing when you're putting it on a table. All of those are derivatives. So it's kind of amazing that this is such a simple but practical idea is to find derivatives. Tan minus 1 of u, I see that first. And I'm recognizing that it is not tan, it's arctan. Arctan, Julia told me it's 1 over 1 plus input squared, or input squared plus 1. So it's going to be 1 over u squared. Either keep it like this and rewrite it later, but I don't. I know it's going to be e5x, e to the 5x squared. Does this step make sense? I think when you get used to this, after this, it's getting better. And then you don't stop. You do times that chain rule. Derivative of the function inside. E to the 5x gives you e to the 5x times 5. So this is chain rule with chain rule with chain rule. And it still repeats all the previous material. And that's why I told you have to be good with chain rule right away, or after that, or maybe 2 weeks after that. But at some point, it'll be too late. We're going to get into so much complicated material that if you don't know chain rule, you're kind of basically screwed. Arccosine, let me repeat this one because I recognize something like this on the quiz today. Arccosine is at arccosine at 8 to the x. How about that one? 8 to the x. Y prime equals. Okay, your arccosine, Julia told me don't remember arccosine. She says remember arcsine and then put minus on top of it. I can do that. So minus 1. And then remember arcsine and arcsecant has 1 over square root. And then one of them is input squared minus 1. Another one is 1 minus input squared. So which one it is? Because sine is v1 then you put 1 first. I don't know, like some kind of stupid way. Try to just remember it somehow. 1 minus, or use triangle. 1 minus input squared times u prime, right? And I'm not gonna write this down. I will instead actually put that u is 8 to the x. 8 to the x, and it is squared. So that's why I'm saying out loud. 1 minus input squared, whatever the input is. Then chain of sense times, now take derivative of the function inside. But derivative of a to the x is a to the x, because exponential function copies itself. But because it's not e, you have to fix it by multiplying by natural log of the base. And if it's a log base, not e, then you divide by the natural log of the base. Is that it with this problem or no? The more chain rule? Do you all agree? So some people very confident, other people like, you need to be good at this because we're going to be testing you on this like crazy. Basically, as I understand, this school wants to fail you from this class if you don't know your derivatives. That's why mastery exam is there. It just checks you cannot pass this class without derivatives. So you're not supposed to pass it, or else you will fail the next one right away. You basically, some people drop the next class in a second week because they understand they're not ready. Yeah?
What happens to the cosine?
Oh, cosine. This is arccosine. Yeah, thank you for asking. This is arccosine. You can also write it down as cosine minus 1 of 8 to the x. And then you go to the table, or hopefully you remember. Cosine of minus 1 of u prime is, there's a formula, minus 1 over a square root minus u squared. Square root 1 minus input squared. And then since u is a function times u prime. That's not part of the formula, that's just chain rule. So arccosine goes away because derivative of arccosine is a fraction. So it doesn't even become sine or anything else. Did it make sense? Those are the weird formulas. Very good, very nice for asking that.